Hello, students. I'm Saima Khan. I'm taking today's topic sampling theorem, and this topic belongs to Unit 5th of Digital System for the subject code CS304, and especially CS304 subject is for the computer science engineering student. In this topic, we will understand what is sampling and what are the different types of sampling. So, sampling is defined as the process of measuring the instantaneous value of the continuous time signal in a discrete form. Sample is a piece of data taken from the whole data which is continuous in the time domain. When a source generates an analog signal, and if that has to be digitized having zeros and ones, that is low and high, the signal has to be discretized in time. This discretization of analog signal is called as sampling. The following figure indicates a continuous time signal xt and a sample signal xst. When xt is multiplied by a periodic impulse train, the sample signal xst is obtained. So in the waveform, we are able to see we have the one continuous time signal, that is continuous xt, and in the next, that the below pulse diagram, we have xst, which is the sampled form of the xt. These sampled signals are collected from the continuous time signal data what we have in the xt. Next is the sampling rate. To discretize the signal, the gap between the sample should be fixed. The gap can be termed as sampling period Ts, and sampling frequency is equals to 1 upon Ts, that is the time of sampling, which is equal to the Fs, called as sampling frequency, where Ts is the sampling time, Fs is the sampling frequency or the sampling rate. Sampling frequency is the reciprocal of sampling period. This sampling frequency can be simply called as sampling rate. The sampling rate denotes the number of samples taken per second or for a finite set of values. For an analog signal to be reconstructed from the digitized signal, the sampling rate should be highly considered. The rate of sampling should be such that the data in the message signal should neither be lost nor it should get overlapped, and the rate was fixed for this, called as Nyquist rate. Now what Nyquist rate tells us? Suppose that a signal is band limited with no frequency component higher than W hertz. That means W is the highest frequency. For such a signal, for effective reproduction of the original signal, the sampling rate should be twice the highest frequency, which means Fs is equals to twice of W, where Fs is the sampling rate, W is the highest frequency. This rate of sampling is called as Nyquist rate. A theorem called sampling theorem was stated on the theory of this Nyquist rate. So what sampling theorem tells us? The sampling theorem, which is also called as Nyquist theorem, delivers the theory of sufficient sample rate in terms of bandwidth or the class of function that are band limited. The sampling theorem states that a signal can be exactly reproduced if it is sampled at the rate Fs, which is greater than twice the maximum frequency W. To understand this sampling theorem, let us consider a band limited signal, that is a signal whose value is non-zero between some W and W hertz. Such a signal is represented as xf equal to 0 for f greater than W. For the continuous time signal, the band limited signal in the frequency domain can be represented as shown in the following figure. Here we have designed one band limited signal whose frequency is extended from positive omega to negative omega. We need a sampling frequency, frequency at which there should be no loss of information even after the sampling. For this, we have the Nyquist rate, that the sampling frequency should be 2 times the maximum frequency. It is the critical rate of sampling. If the signal xt is sampled above the Nyquist rate, the original signal can be recovered, and if it is sampled below the Nyquist rate, the signal cannot be recovered. The following figure explains a signal if sampled at higher rate than twice of omega, yeah, w in the frequency domain. So what we are able to see, the figures, all the waveforms are located at some distance. This is because the sampling rate is greater than twice of omega. The above figure shows the Fourier transform of a signal XST. Here, the information is reproduced without any loss. There is no mixing up and hence recovery is possible. The Fourier transform of the signal XST is shown below, where Ts is the sampling period and omega angular frequency is 2 pi a by Ts. Let us see what happens if the sampling rate is equal to twice the highest frequency, twice omega. That means Fs is equals to 2 of omega, where Fs is the sampling frequency and Fs is the highest frequency. And here we are able to see that the waveforms are produced in continuous way without any gap. Now, this is the right presentation of the signal. The result will be shown in the above figure. The information is replaced without any loss, and this is also a good sampling rate. Now let us look at the condition given below. The resultant pattern will look like the following figure. They are overlapping with the neighboring ones. We can observe from the above pattern that the overlapping of the information is done, which leads to mixing up and loss of information. This unwanted phenomenon of overlapping is called as aliasing, in which higher frequency component overlap with the lower frequency component. So, aliasing can be referred to as the phenomenon of higher frequency component in the frequency of the signal taking on the identity of lower frequency component in the spectrum of its sampled version. The corrective measures to reduce the effect of aliasing are: in the transmitter section of the PCM, a low pass anti aliasing filter is employed before the sampler to eliminate the high frequency component which are unwanted. The signal which is sampled after filtering is sampled at a rate slightly higher than the Nyquist rate. If choice of having the sampling rate higher than Nyquist rate also helps in easier design of the reconstruction filter at the receiver. So student, this is all for this presentation. We will meet in the next presentation. Thank you students. Thank you so much.